Bismillahirrahmanirrahim. Dear students, today's our lecture is about Chichibabin pyridine synthesis. Basically, it is about the formation of carbon-nitrogen bond. But here in this case, the bond formation is in such a way that we get the heterocyclic six-membered ring bearing nitrogen, and also in aromatic way, and so therefore due to formation of aromatic six-membered nitrogen bearing ring, we call it pyridine. So this reaction is also overall known as Chichibabin pyridine synthesis. The key points of today's lecture are: number 1, introduction to Chichibabin reaction pyridine synthesis, then overall mechanism with respect to ammonia, and then overall mechanism with respect to amide in the presence of ammonia. Also the explanation of the mechanism step by step, and then we shall discuss the limitation of this reaction and some synthetic applications of this reaction in today's lecture. Chichibabin pyridine synthesis was given by Chichibabin in 1924. This method was used to synthesize the pyridine ring. It is about the condensation reaction of aldehydes and ketones, or aldehyde alpha beta unsaturated carbonyl compounds, aldehydes or ketones, or in any combination of these with ammonia or ammonia derivatives. Combination mean there you can use one aldehyde with ammonia, one ketone, one alpha beta unsaturated aldehyde or ketone, or more than one, that is aldehyde and ketone both are present as a substituent. Then we can get a number of products with a number of variety of pyridine structures. You can see the overall reaction. First is about the three molecules of aldehyde reacts with ammonia through the formation of pyridine, and you can see the different substituents present in the pyridine ring are at number 2 position, 3 position and 5th position. 2, 3, 5 tri-substituted pyridine ring is produced in this reaction, and the reaction condition can be moved through the use of only ammonia or through the use of sodium amide and ammonia, and we get the product. First of all, overall mechanism is given with the ammonia. Aldehyde, one molecule of aldehyde is interacted with the ammonia. Nucleophilic ammonia interacts with the carbonyl of aldehyde, and we get the oxygen with negative charge, and then this negative charge abstract a proton from this ammonium and make it NH2, and we get the product. In the second step, another molecule of ammonia acting as a base abstracts proton, and we get the double bond here between alpha and beta carbons with the removal of OH group in the form of water, and we get the enamine, which after tautomerism can be converted into imine. The second molecule of aldehyde in the presence of base ammonia give out the proton and gets the negative charge on this alpha carbon, and this acidic proton is removed by the ammonia. This alpha carbon is acting as a nucleophile, attacks on the another aldehyde molecule and moves through the aldol condensation mechanism, and we get the product of aldol condensation product having aldehyde functionality and alcohol functionality. Then after the removal of water, we get the double bond here in this aldol product. This aldol product after getting double bond, that is normally it is also termed as a crotonaldehyde. This crotonaldehyde type molecule is then interacted with the imine moiety. The nitrogen of imine acting as a nucleophile attacks on the carbon, this beta carbon, and the double bond of alpha beta moves towards the carbonyl, and the double bond of carbonyl gets the single and oxygen gets the negative charge, and this product is also known as Michael addition product. Then ammonium already present in the medium comes here and gives the proton to this alkoxide ion, and we move towards the next slide where we discuss about this step. As we discussed in the last slide, the aldol protonaldehyde type product interacts with the imine. The nucleophilic amine attacks on the beta carbon, double bond moves towards the carbon, and oxygen gets the negative charge, and when this negative charge moves back, then the double bond moves towards the alpha carbon, and that alpha carbon, acting as a nucleophile, abstracts the proton from the you can say acting as a base, mainly it should be said base, abstract the proton from ammonium, and we get this type of product here. In the next step, the ammonia again acting as a base abstracts the proton from this imine part at alpha beta carbon of imine part, and again we get the double bond here. The double bond of carbon nitrogen moves towards the nitrogen with lone pair at nitrogen, and we get a simple amine here. And in the next step, again this nitrogen lone pair acting as a nucleophile moves towards the alpha carbon and making it double bond. The carbon alpha beta carbon double bond is interacting as a nucleophile from beta side and attacks on the carbonyl carbon of aldehyde, and the carbonyl double bond is converted into single bond or oxide ion, then abstracts proton from the ammonium ion, and we get a cyclic product in which nitrogen bearing one double bond attached with one double bond, and also this 6-membered ring bears a hydroxy group. After the removal of water, we get another double bond, and then after auto oxidation 2 protons have also been removed, and we get the aromatic ring formation, and this is the pyridine. So in this way, overall the cyclic 6-membered pyridine has been formed. Here you can see the other mechanism with respect to amide and ammonia. First is the imine formation. Here you can see the interaction of aldehyde with amide. In this case, amide acting as a nucleophile attacks on the carbonyl, oxygen gets the negative charge, and this negative charge gets one proton from the ammonia, and NH2 amide ion is produced. This amide ion abstracts the proton from the beta carbon, and we get the double bond here in amine, and which is move under tautomerization towards the imine. Second step is the aldol condensation. In aldol condensation, one aldehyde molecule is interacting with the amide functionality, which is acting as a base. It is activated by the removal of the proton, and this activated interacts with the other nucleophile through its carbon, other electrophile, sorry. This nucleophilic carbon attacks on the other aldehyde molecule, and through its carbon acting as a nucleophile, and we get the aldol condensation product, and which after the removal of hydrogen and from alpha position and water, we get the double bond, that is crotonaldehyde type molecule is generated. In the third step, which is pyridine synthesis, there is Michael addition between the imine, previously found imine from one molecule, and this crotonaldehyde found from these two molecules, and we move in such a way that imine nitrogen of imine acting as a nucleophile attacks on the alpha beta carbon, double bond alpha beta moves towards the carbon, and oxygen gets the negative charge. This negative charge moving back, double bond acts as a nucleophile base and abstracts the proton from the beta position of the imine, and then we get the double bond here, and nitrogen gets its lone pair back. In the next step, lone pair moves again towards the alpha carbon, and carbon attacks through its beta position to carbonyl acting as a nucleophile, and cyclic ring has been generated. The oxygen gets the negative charge, and which is protonated by the ammonia. And then after the abstraction of proton by the amide, we get the double bond here with the removal of water, and in the last step 2 protons are also removed by the amide or ammonium function that is through auto oxidation by these basic moieties, and we get the formation of the pyridine here. Here is the second step-by-step mechanism of this reaction. First we discuss the imine formation. Here the discuss mechanism with respect to ammonia NH3 molecule. Here you can see first the ammonia acting as a nucleophile attacks on the carbonyl carbon of aldehyde, making carbon oxygen double bond single, and oxygen gets the negative charge. This is simply nucleophilic addition reaction of aldehydes, carbonyl compound, and ammonia. We have discussed in last lectures also that aldehydes or ketones go through the nucleophilic addition instead of nucleophilic substitution because they do not have the good leaving group. So therefore whenever a strong nucleophile attacks on the electrophilic center of this carbonyl carbon, then oxygen gets the single bond, and that is there is simple addition on this carbon oxygen double bond, and we get an addition product with carbon oxygen single bond formation. After the attack of this ammonia on carbon, we get the ammonium formation, nitrogen with positive charge and oxygen with negative charge. Then this oxygen can abstract proton from this nitrogen, which is at its vicinal position. So vicinal proton is stereochemically approachable, so it is easily removed, and nitrogen positive charge of nitrogen is finished, and also the oxygen negative charge of oxygen is balanced. We get the product in which amino group and hydroxy group are present at the same carbon. In the next step there can be two types of pathways. One is the intermolecular, second is the intramolecular. Here we first discuss the intramolecular, in which lone pair of oxygen attacks on the vicinal hydrogen, that is at beta carbon, and we get the double bond between alpha and beta carbon, and OH after protonation is converted into water, H2O, a good leaving group, so it is removed from this carbon, and we get the carbon-carbon double bond here. This type of molecules are known as enamine, that is that is alpha and beta carbon of an amine are unsaturated. Or you can say it is alpha beta unsaturated amine, which can move through tautomerism, and after tautomerization process we can get another form which is known as imine form, in which carbon nitrogen bond is double bonded and the alpha beta bond is now saturated one. The formed water can interact with the ammonia, and we can get the ammonium hydroxide because water easily attach with the ammonia with the formation of ammonium oxide in a reversible manner. Second is the intramolecular interaction. In this first step is the similar, that ammonia attacks on aldehydes, oxygen gets the negative charge, then this negative charge is counterbalanced by the abstraction of proton from vicinal position, and nitrogen is balanced with its lone pair, and oxygen is also balanced with the attachment of this proton. And now the ammonia attacks on this beta proton. You can see the proton attached to that carbon which is at beta position from the amino or hydroxy group. So this beta proton is abstracted by the ammonia with the formation of ammonium ion, and this proton carbon hydrogen double bond is moved towards the carbon alpha beta carbon, where double bond is formed, and at the same time OH minus group is removed, which is attached with the ammonium in the form of ammonium hydroxide. I have omitted some steps here because you know that in simple alcohols the OH group is not a good leaving group. First it has to be converted into a good living group like water, H2O, then it will be removed easily. So here this step has been omitted. You can imagine, or you can consider it that this OH group will be omitted by in the form of water. That water interacts with the ammonia, and so formation of ammonium hydroxide has been achieved. The resulted imine moves through the tautomerization and we get the imine product. The operation of this tautomerization process, you can see the carbon nitrogen is partial negative charge, and the alpha carbon is partial positive charge, and the beta carbon will be partial negative charge. If nitrogen is partial negative, then the hydrogen attached to this nitrogen will be partial positive charge. Now the beta partial negatively charged beta carbon will attack on the through its pi electron on this proton, and the two electrons from this hydrogen and nitrogen moves towards the carbon nitrogen, making their double bond, and the double bond is moved towards the beta carbon, which is actually interacting with through the proton. So in this cyclic way we get the imine formation. Here the second step of aldol addition. Here you can see the ammonia acting as a base abstracts the proton, that is alpha proton of the aldehyde functionality, and you know, due to electrophilic character of this carbonyl group, the alpha carbon is acidic in nature, and here the proton can be abstracted in the form of proton, and the resulting, and it will easily remove the proton because the resulting anion is resonance stabilized. That is, after the abstraction of ammonia proton by the ammonia, we get ammonium, and the carbon hydrogen two electrons are moved towards the carbonyl, and double bond of carbonyl is broken, and we get the oxygen with negative charge. This negative charge oxygen is balanced by the formed ammonium cation. This anion, this alkoxide or enolate ion is resonance stabilized. Here you can see its resonating structure. Oxygen moves towards the carbon, and double bond moves towards the alpha carbon, and there is negative charge on the alpha carbon, which is also balanced by the ammonium ion. So this enolate or you can see alkoxide, you can see anion, this anion act as a nucleophile, and it acts as a nucleophile on the second molecule of aldehyde for the formation of aldol product. Here is a question: which of the following two species will be more stabilized? That resonating structure in which carbon is given negative charge, or that in which oxygen is given the negative charge? Then you will see that that form is more stabilized in which oxygen is given the negative charge, because number one, there is the most electronegative element is with the negative charge. This is a stabilized form of a resonating structure. So therefore the more contributing structure will be this enolate structure, and when this acts as a nucleophile, it attacks in this manner that oxide ion oxygen moves negative charge of oxygen moves towards the carbon, making double bond, and the carbon carbon double bond moves towards the alpha carbon, which acting as a nucleophile attacks on the carbonyl carbon of other aldehyde molecule, and the double bond is broken into single bond, and oxygen gets the negative charge. We get this product, and this negative charge is also counterbalanced by the ammonium cation, which was already present with it. And now this oxide ion can abstract proton from this ammonium ion, making the ammonia free, and we get the aldol product. Aldol because it contains aldehyde functionality and also the alcohol functionality, so it is termed as aldol. In the next step is the removal of water, and the removal of water can be proceeded in this manner that the oxygen OH, lone pair of OH oxygen in OH group acting as a nucleophile, attacks on the hydrogen, vicinal hydrogen at alpha position, which is acidic in nature, and the carbon hydrogen two electrons move towards the alpha beta carbon, making their double bond, and OH group is removed in the form of water, and we get the alpha beta unsaturated carbonyl compound. This alpha beta unsaturated carbonyl compound is then used for the last step of for the next step. The formation of this alpha beta unsaturated product can be proceeded another way. Here you can see the second way, in which first the step is the same as the attack of ammonia for the formation of anion, which acting as a nucleophile attacks on the aldehyde, and we get the product in the form of alkoxide, which gets proton from ammonium, and we get the aldol product. This aldol condensation is converted into alpha beta unsaturated moiety in this way that it moves through the intermolecular interaction. The last step, the first was the intramolecular. Here is the intermolecular, in which ammonium, or you can say ammonia, acting as a nucleophile, abstract the proton, and carbon hydrogen double bond moves towards the carbon, making their double bond carbon hydrogen single bond, two electrons two sigma electrons move towards the alpha beta carbon, making their double bond, and OH group is removed in the form of water, and this water attaches with the ammonia to form ammonium hydroxide. Here also you can see the OH group is not a good living group, it will be removed, but in the form of a water. So in this way we get the alpha beta unsaturated carbonyl compound. Here is the step 3 for Michael addition, in which the alpha beta unsaturated carbonyl compound is added to the imine. Here's the first thing that we first demonstrate the mechanism. The lone pair of nitrogen in imine, acting as a nucleophile, attacks on the beta carbon, double bond is moved towards the carbonyl carbon, and oxygen gets the negative charge with the breakage of pi bond. And in the product side, nitrogen gets the positive charge due to formation of 4 bond, and oxygen gets the negative charge. Ammonia molecule comes, which abstracts this proton from nitrogen, and positive charge of nitrogen is counterbalanced, and the negative charge of oxygen remains as such, which is counterbalanced by this newly formed ammonium ion. Here is the first question in this first step of reaction, is that nitrogen is carbon in the form of carbonyl, that is carbon, likewise carbon double bond oxygen. So here is carbon double bond nitrogen. Nitrogen is sp2 hybridized, and simply oxygen is sp2 hybridized. Also the two oxygen has lone pair, and here nitrogen has also lone pair, but the attack is from this lone pair, nitrogen lone pair, on the beta carbon, unsaturated beta carbon, not from the lone pair of oxygen on the carbonyl of this imine. This thing can be explained by number 1, that nitrogen is more nucleophilic as compared to oxygen, so therefore nitrogen will act as a nucleophile, and we will get the nucleophilic attack from this nitrogen of imine towards the beta carbon. Second is thing, if there is possibility, if we let's suppose that oxygen lone pair attacks as a nucleophile on the carbonyl, or you carbon double bond, carbon of carbon double bond nitrogen double bond, then the formed product is not much stabilized. If you draw the structure of the molecule, you will see that there is much distribution of charges, and much you can see in too much unstable form. So therefore due to instability of product, this reaction is not favored. Number 2 and number 1, more nucleophilicity of nitrogen moves this compound through this way. Second question is that why attack is on this beta carbon, not on the carbon of aldehyde group. This thing can be explained in this way that the carbon alpha beta double bond is resonating towards the carbonyl, and so due to this resonance towards carbonyl, the electrophilic center of carbon has been decreased too much, and also this carbon is shielded by the pi electrons which are conjugating on these 4 atoms, 1 oxygen and 3 carbon atom. So there are but this beta carbon is open from one side, and so therefore it is easy for this nucleophile to attack on this beta carbon due to less steric hindrance and also more electrophilic character. So we get the product which on attack with by the ammonia, we get the next product in which we only have enolate structure. This enolate can move in 2 ways towards the product. One is shown here that oxygen oxide negative moves towards the carbon making double bond, and double bond moves towards the alpha carbon and acting as a base, it abstracts proton from ammonium, and we get the carbon single bond with the formation of carbonyl group. Second possibility can be, you can see below it, the first 2 steps are the similar one, and here the difference is that this O minus charge can directly attack on the proton of this ammonium cation, and it will be converted into OH, and ammonia is removed as in the last case, and so we will get an enol form which is a tautomeric form of aldehyde. So the product can be formed in this way also. This is the last step of pyridine synthesis. Here you can see the last prepared intermediate is interacting with ammonia. Ammonia acting as a base abstracts the proton from beta carbon, you can say alpha carbon of C double bond N moiety. Here you can see this proton is looking to be acidic one. It is just like that we know that the alpha proton of carbonyl compounds are acidic in nature due to electron withdrawing effect of carbonyl groups. Likewise, this C double bond N acting as like that of carbonyl, then the alpha carbon bearing this proton will be acidic in nature, and it can be easily omitted by a base. So ammonia acting as a base abstract this proton making ammonium ion, and we get the double bond between alpha carbon and the double bonded carbon, and nitrogen gets the negative charge. This negative charge is balanced by the proton of this newly produced ammonium ion, and we get simple neutral molecule. Here can be questioned as why if a proton is abstracted which is acidic in nature, then we have aldehyde group also in this moiety, and the carbon alpha carbon also bears proton here which is acidic in nature. So why this ammonia is not acting as a base for that proton also? Number one, if it abstracts that proton that is from the alpha carbon of aldehyde moiety, then we are moved towards the reactant in the form of enol form of the reactant, and we will not be able to move to the product. Number one thing. Number two thing, there can be hindrance of the groups. No hindrance, I think hindrance cannot be, because it is a open chain. Attack is possible for both, but attack on the alpha carbon of aldehyde functionality moves us towards the reactant side, but this attack moves us towards the product side, so we are attacking on this proton also. So after the neutralization of negative charge of nitrogen, we get the neutral molecule. In this neutral molecule, the lone pair of nitrogen moves towards the carbon of the alpha beta double bond, unsaturated double bond, this pi electron moves towards the second carbon and attacks as a nucleophile on the carbonyl carbon of aldehyde functionality, and oxygen gets the negative charge. In this way we get the formation of six-membered ring. In the next step, the positive charge of nitrogen is counterbalanced, finished by the removal of proton, abstraction of proton by the ammonia, and this ammonium ion is balancing the negative charge of the oxide ion. Oxide ion gets the proton from this ammonium cation, and we get enol, we get alcohol OH group. This OH group removes in a cyclic manner in the form of water, that is lone pair attacks on the hydrogen, and sigma electron moves towards the ring carbon carbon single bond, making it double bond, and the O carbon oxygen bond is broken due to formation of water, and with the removal of water we get a double bond here. In the last step there happens some auto oxidation due to which two protons are also removed at adjacent position, and we get double bond here through the formation of a conjugated structure, that is pyridine. Auto oxidation can be through some peroxide, some peracids, or due to moieties which are present here in this reaction mixture. So we are not going to discuss the detail of this auto oxidation. Simply I am mentioning here the formation of auto oxidation here. Here are some limitations of this reaction. First is the low product, and this low product is because of a number of byproducts which we have to remove to get the final main pyridine product in purified form. So therefore due to a large number of purification steps we get the percentage yield of the final product too much low. Also the high number of high proportion of these byproducts can be due to aldol condensation, or can be due to carbonyl chemistry. In addition to this there are a number of byproducts also are side reactions. First is imine formations. In the imine formation step, the nucleophilic attack of ammonia at the beta carbon lead to another product. If the attack is at alpha carbon, then enamine or imine formation occurs, but attack at beta carbon gives some other types of products. Similarly, nucleophilic attack of ammonia on the enamine or imine, which is not the part of the mechanism, this attack can lead to a number of side products. Second was the aldol condensation step. At this step for asymmetric ketones, the abstraction of non-preferred beta hydrogen led to side products. Enolate attack, ion attack of the enamine or imine carbon. When attack is given by enolate ion on the enamine or imine carbon, it will lead to side products. Also enolate ion attack of an unintended aldehyde or ketocarbonyl. This will lead to the formation of side products. In the last pyridine synthesis steps, there was imine attack of carbonyl rather than gamma carbon. This is side reaction. Similarly, imine attack at an enamine or imine carbon, and in the end in case of simple aldehydes, particularly in the case of alpha beta unsaturated carbonyl compounds, polymerization of starting material can also occur. So these are the number of side reactions which make the use of this reaction limited. Here are some ways to overcome this limitation. First is the protection of carbonyl increases product yields. That is, we can use the protecting group. Second, the use of peraldehyde as source of gradually available aldehydes for the reaction can limit the different side reactions. Also, the large excess of aqueous ammonia, about 3 equivalents, with catalytic amounts of ammonium acetate can also minimize the side reactions. Conducting the reaction in gas phase and passing over a number of catalysts including aluminium 3 oxide, which gives yield about to 65% at 600 Kelvin, or zeolite giving 98.9% yield at 500 Kelvin, and many others. A normal yield, never exceed about 40%, never exceed the 40% yield in normal cases. But these catalysts, these conditions have make this reaction to move to 65% yield and also to 98.9% yield. Also, the increasing pressure and temperature conditions, we can limit the formation of side reactions and can achieve high yield of the product. As we have discussed, due to a large number of side products and limit of percentage yield, this reaction is not synthetically appreciable. But there are some examples in which this reaction has been studied in some specific conditions. Actually, I am not discussing its synthetic application. I am discussing some types of its modes of reaction which have been proceeded for this reaction, this pyridine synthesis reaction. First is, you can see the use of aldehyde and formaldehyde. Can be cross aldol product acrolein, or there can be self aldol product crotonaldehyde, which interacts with ammonia forming the different products. So number of products have been achieved. Likewise, benzaldehyde, acetaldehyde in the presence of ammonia gives 3 different types of pyridine molecules. And if we use simple single aldehyde in ammonia, but in the presence of aluminum oxide, we get 2 types of products, but one type is major one, about 60%. So this is the brief description of the different nature of products, different types of products which have been achieved in different conditions for this reaction. So this is all about of today's lecture, and thanks.